We've already talked about one reason why we care about momentum, and that was the idea of impulse, and we can link that to force. But there's another reason why we care about momentum, and that is conservation of momentum. So, if there are no outside forces acting on a system, and that is the key qualification here, then the total momentum of the system is conserved. So we remember from the energy unit that conserved means that a quantity does not change. Okay, so if we have a system of more than one object, okay, and there's no forces on that system other than the forces that the objects exert on each other, then the total momentum of the system is going to be conserved, is going to stay the same. And this is really useful when we look at systems where the objects are colliding together or exploding apart, when the objects start together and move apart from each other. This idea of conservation of momentum is going to help us to analyze those systems. So let's take a look at a quick example of this in action. We have a system here of a blue car and a yellow car, and the blue car eventually collides with the yellow car. So let's look at the momentum before and after. So before the collision, the blue car has a momentum of 2,500 kilogram meters per second, just mass times velocity, and the yellow car has a momentum of 800 kilogram meters per second, giving us a total momentum for our system of 3,300 kilogram meters per second. Now, after the collision, we see that the blue car is going to have a momentum here of 1,500 kilogram meters per second, and the yellow car is going to have a momentum of 1,800 kilogram meters per second. And if we bring those two together, we see that the total momentum of our system is still 3,300 kilogram meters per second. So it does not change. That's the idea of momentum being conserved. Another thing we can think about that kind of links us back to impulse is the blue car had a change in momentum of negative 1,000 kilogram meters per second. The yellow car, on the other hand, had a change in momentum of positive 1,000 kilogram meters per second. So whatever momentum that one object gains is the momentum that the other object loses. And the reason for that is, keeping in mind that momentum is force, or average force, times change in time, we know that these two objects are going to exert equal and opposite forces on each other. And that means that their changes in momentum, because the forces are the same, just opposite signs, and the times are the same, their changes in momentum will also be equal and opposite. So whatever momentum one object gains, the other one loses, and the total momentum of the system stays the same. Equation-wise, our equation for conservation of momentum is very basic, just that the initial momentum of the system, pi, adding up all the momentums of the individual objects, equals the final momentum of the system, pf. And so we're always going to be thinking about, we talked about initial and final, we're always going to be thinking about before and after our collision or explosion, because those are really the two cases when we're going to use conservation of momentum. A few tips here about using conservation of momentum. The first thing, and this obviously is the most important one, is use conservation of momentum when we have a situation where momentum is actually conserved. And that's going to be collisions or explosions with no outside forces. So the only forces that should exist are the forces that are acting between the objects in your system. We're always going to start with that equation here for conservation of momentum, pi equals pf. And much like energy and forces, this is going to be one where you're starting with that base equation and you kind of have to make your own equation from there. You're going to be filling in the momentum of what objects have momentum in your system before and after the collision. Okay, and that's really the key. Negative signs are a big one here. They're always a big one, but they're especially big here. We do need to indicate if velocities are in the opposite direction using a negative sign, because momentum is a vector, and we do need to be aware of the direction of the momentum of an object. Let's go ahead and work through a few conceptual questions here. So for this first one, we have a situation where there's two boxes with a spring in between them. The spring's initially compressed, the boxes are at rest, and we're going to release the spring, setting the boxes in opposite directions. And the question asks which box is going to have the greater momentum after the spring's released, and the answer is they're going to have the same momentum. And our reason for this is that our initial momentum of our system is going to be zero. Okay, neither object is moving initially. So when they release and are sent in opposite directions, that final momentum still has to be zero. So how is it that we have two objects moving, but their final momentum is zero? The final momentum of the system is zero. The only way that happens is if they have the same momentum, but they're moving in opposite directions, and therefore the signs of their momentum are opposite. For part B of this question, it asks which box has a greater kinetic energy when the spring is released. And the answer for this one is going to be box A. There's two ways of thinking about this one. The first is that since they have the same momentum, but box B has more mass, that means that box A must have the greater velocity. And we know that kinetic energy is proportional to 1/2 mv squared. So since the velocity term is squared, having that greater velocity, having twice as much velocity, actually means a greater kinetic energy than B, where the mass is twice as much, but that mass term is not squared. The other way we can think about it is the forces are the same, but since box A has a smaller mass, it will move a greater distance while the spring is releasing, and that means more work is going to be done on box A, and therefore box A will have a greater kinetic energy. For this next problem, we have a bullet that's going to be fired at a block, two identical bullets actually that are going to be fired at a block. And in case A, the bullet becomes embedded in the block and the two slide off together. In case B, the bullet hits the block and then is going to rebound back in the opposite direction because it's a rubber bullet. And we want to know in which case is the velocity of the block after the collision going to be greater. So the answer here is going to be in case B, and I think the easiest way to think about this one is to consider the change in momentum of the bullet. In case A, the bullet is traveling to the right at some speed, and then when it embeds in the block, okay, it's going to slow down, all right, as that system of bullet and block continue traveling to the right. In case B, however, the bullet's initially traveling to the right, it rebounds off of the block and now is traveling back in the opposite direction. So we're going to have a greater change in momentum in case B. Since we know that momentum is conserved, whatever the change in momentum of the bullet is, that's equal to the change in momentum of the block. That's the only way for the momentum of the system to be conserved, is if whatever one gains in momentum, the other one loses. So in case B, the change in momentum is bigger for the bullet, which means the change in momentum is bigger for the block, and therefore the block is traveling faster. So we have one more conceptual question here about two objects that are initially moving in opposite directions, like we have here. And we see a graph here of their velocity versus time. So there's object A initially moving in the positive direction, and object B initially moving in the negative direction. The two objects then are going to collide, and they're going to stick together as one unit. And ultimately they end up moving in the positive direction, which is what we see right here. So the question asks, which one has a greater mass? The answer here is going to be cart A, and there's a few different ways of thinking about it, but I think the easiest way is to think about, first of all, the change in velocity of each cart. So if we look at cart A, that's the change in velocity of cart A. Cart B clearly has a much greater change in velocity. Now, knowing that the momentum of the system is going to be conserved, that means the change in momentum of each cart has to be the same. So, if A has a much smaller change in velocity than B, A must have a greater mass. And that really goes back to one of our definitions for impulse, the fact that the impulse, the change in momentum, is mass times change in velocity. If we have a really, really small change in velocity, it must mean we must have a bigger mass in order to have the same change in momentum, and that's the case here. The other way we can look at it is cart A initially had momentum in the positive direction, with a small velocity. Cart B initially had momentum in the negative direction. Ultimately, the two objects travel in the positive direction. So that means that A has to have more momentum than B. And since it's traveling slower than B initially, that means it must have a greater mass than cart B. Let's go ahead and do a math problem with this. So we have this problem where Alex once saw a red car with a mass of 2,100 kilograms traveling the wrong way down Gay Street until it hit a 2,900 kilogram blue car that was initially at rest. So the velocity of the blue car was initially 0, and we're told the velocity of the red car was initially 5 meters per second. Then we're told that the red car rebounds at a speed of 0.5 meters per second, and we want to figure out the velocity of the blue car after the collision. So now that we have a basic idea of what's going on in this situation, I'm going to set up my conservation of momentum equation. Momentum initial equals momentum final. So I'm going to think about what is momentum before the collision, and I'm going to call the red car object 1 and the blue car object 2. So before the collision, we have the red car. So its mass times its initial velocity. So I'll call that V1 initial. After the collision, we're going to have both objects moving. So we're going to have the mass of object 1 times its final velocity is going to be one component of our final momentum, and then we're going to have the mass of object 2 times its final velocity. Now we can go ahead and plug in the numbers we have here for the masses and the velocities of each object. So we know the mass of the red car is 2100. We know its initial velocity is 5. Its final is going to be negative 0.5. I need to indicate that sign there. And for the blue car, its mass is 2900, and I'm just going to leave that as a variable there, V2F. That's what I'm ultimately solving for. So when I go ahead and do my math here, I find that my final velocity for car 2 is 3.98 meters per second. The next part tells me the collision lasts for 0.4 seconds. We want to find the average force on the red car. So for that, I'm going to think about my change in momentum, which is mass times change in velocity. So the change in momentum of the red car is going to be 2100 times final velocity, negative 0.5, minus initial velocity, which is 5. And so I end up getting a change in momentum here of negative 11,550 kilogram meters per second. Now that I have that, I can go ahead and solve for my average force using the fact that change in momentum is also average force times change in time. So that negative 11,550 is going to be equal to the average force times 0.4 seconds. And so I end up getting an average force here of negative 28,875 newtons. Now the negative sign there, depending on how you set things up, that just really indicates the one direction, and it's based off of what I chose as the signs for my initial and final velocities. If I had said the red cart was initially traveling in the negative direction, I would have gotten a positive force there. So usually we're just going to be concerned with the magnitude, but based off of how I solved it, it's going to end up being negative. Now for the blue car, we're going to do the exact same thing. The change in momentum is mass times change in velocity. So for the blue car, it's going to be 2900 times 3.98 minus 0. And if you used your unrounded numbers, you get a change in momentum here of 11,550 kilogram meters per second. And then we can go ahead and solve for our average force using the fact that change in momentum is average force multiplied by time. So 11,550 equals our average force times 0.4. And so we get an average force here. And again, this is if you used unrounded numbers of 28,875 newtons. Folks, this is not a coincidence at all that these two numbers are the same. And this really comes down to Newton's third law. The objects exert equal and opposite forces on each other, and these two numbers, the changes in momentum, also happen to be the same, and that really comes down to the fact that momentum is conserved, right? The change in momentum of the two objects must be equal and opposite so that the total change in momentum of the system is 0. It stays the same before and after the collision. Just a quick side note, because we saw this in the last problem, we saw applications of both of the important parts of momentum, both impulse and conservation of momentum. So just a quick note about when we're going to use them. Conservation is mainly going to be for collisions or explosions between 2 or even 3 objects. All right. Impulse, on the other hand, is going to allow us to analyze the average force or the force versus time graph when we're talking about a single object. So for this next problem, we have a situation where Maddie's going fishing with her sister on a boat. So here's the boat, here's Maddie, here's the sister. And they're initially at rest here. And what ends up happening is Maddie decides to throw her sister off the boat at a speed of v. We're ultimately going to be determining the recoil speed, the speed that the boat and Maddie go backwards, and we'll talk about why that happens in a second. We also know that the sister has a mass of m, and Maddie and the boat combined have a mass of 4 times that much, so 4m. So we're going to go ahead and set up our conservation of momentum for this system. There's no outside forces, so we can use that. Initially, there's no momentum in our system because nothing's moving. And then afterwards, both Maddie and the boat together and the sister are going to have momentum. So we can go ahead and plug in what we know about each of those objects. So this is going to be 4m times v1f, which is what we're solving for, plus m times v. We can cancel out the m's here, and we can solve for v1f, and we get that v1 final is going to be negative v over 4. It does say speed, though, so we can make this positive because speed is technically the magnitude of the velocity, so we just say v over 4. Next question, part B, asks us to explain using forces why the boat moves when her sister is thrown. And the main idea there is Newton's third law, that when Maddie exerts a force on her sister exerts a force back on Maddie and the boat, causing both of them to move. For part C, we want to explain it in terms of momentum, and so for that we're going to think about the fact, and we can look at our equation to see this, that our initial momentum was 0, so afterwards the two objects have to have equal momentum in opposite directions, and that way the final momentum of the system will still remain 0 because momentum is conserved. Moving on to part D here, this situation where we have this graph here of the force exerted on Maddie's sister while she's being thrown, the maximum force being F here. And we want to derive an expression for the time over which the force was exerted. What I'm going to do is I'm first going to solve for my impulse using what I know about Maddie's sister. So the impulse is going to be the mass, which is just m, times the change in velocity, v minus 0. So the impulse is just mv. Now we can use the fact that the impulse is also the area on that graph that we have above. Okay, and so we can say the impulse is going to be 1/2 our time, which we're solving for, times f, which is the height up here. And so we set those two equal each other. We're going to say mv equals 1/2 times the time times the force. And when we go ahead and solve for time, we get the time is going to be equal to 2mv over that force. And the last piece here is we just want to draw a graph of the force exerted on the boat and Maddie on the same graph here. So that's going to end up being basically just the flip of our original graph. So it's going to go down, reaching a peak, and then go back up. Just a mirror image flipped over the x-axis. All right, moving on to this next problem here. We have a block sliding down a ramp. It's going to eventually collide with a stationary block at rest, and then they're going to slide off together. Okay, and so we have a few questions. First of all, we want to know during what period of time is momentum conserved and during what period of time is energy conserved, and we want to explain that briefly. So what we want to keep in mind is our two qualifications for when momentum and energy are conserved. Momentum is conserved if there's no outside forces. So while this block is sliding down the ramp, okay, it's clearly gaining momentum. Our system's clearly gaining momentum because nothing's moving and then all of a sudden this block's moving. And the reason is we have an outside force from gravity pulling down on this block. However, during the collision and afterwards, momentum is going to be conserved because there are no outside forces. Energy is conserved when there's no non-conservative forces. And so, as the block's sliding down the ramp, energy is conserved, okay? But during the collision, energy is not conserved because there are non-conservative forces that the block exerts on each other. And it's an inelastic collision. We saw that in our lab, that in an inelastic collision, energy is lost. Moving on to part B, we ultimately want to know the speed of the two blocks after the collision. Okay, and so what I'm going to do is I'm first going to set up conservation of energy to analyze that one block just sliding down this ramp here. So E initial plus work equals E final. I start with gravitational potential energy, I end with kinetic. So I can say that mgh is equal to 1/2 mv squared. I see that the masses there cancel out, and that means that my velocity at the bottom of the ramp before colliding with the other block is just going to be the square root of 2gh. After I have that velocity, I can think about the collision, and I'm going to analyze that using conservation of momentum. So initially it's just block 1 moving, and then afterwards it's going to be the combination of both blocks moving, and I'm solving for this final velocity here. Okay, I know that the original block has a mass of m. Its velocity is that root 2gh. Afterwards, they combine and stick together, and so it's m plus 2m to get the total mass of the system, since the at-rest box has twice as much mass, times that final velocity. So I have m times the square root of 2gh equals 3mvf. The masses cancel out, and I get a final velocity here for my system of root 2gh over 3. Part C here asks about how much energy was lost, so for that I'm going to consider my energy equation, E initial plus work equals E final, and so we're thinking about the energy lost in the system. So initially I have the kinetic energy of object 1 plus any work done, which ultimately is going to be a negative number, but I'll leave it as plus work for now, and then the final kinetic energy of our two-block system. So initially it's just going to be 1/2 m times that initial velocity, the square root of 2gh squared, and that was that velocity that I got up here, plus the work done is going to be equal to 1/2 times the combined mass, which is 3m, times that final velocity, root 2gh over 3, that entire quantity squared, and that comes from that number there. I can go ahead and do some simplification, squaring those things, so it ends up being 1/2 m times 2gh plus work equals 1/2 times 3m times 2gh over 9, because I have to square top and bottom. I can cancel out a few things here and simplify, so the 1/2 and the 2 cancel out there. The 1/2 and the 2 cancel out here, and that 3 cancels out part of that equation. And so what I'm left with is mgh plus work is going to be equal to mgh over 3, and that means that my work done is negative 2/3 mgh when I go ahead and solve for work. So the last part here, part D, asks how the velocity of the two boxes would change if we doubled the height of the hill. So I'm going to take this equation here, our original final velocity, which was the square root of 2gh over 3, and I'm going to set up our new final velocity, vf prime, and that's going to be equal to the square root of 2g times 2h all over 3. And we can go ahead then and try and combine. What I'm going to do here is I'm going to pull out this 2 right here, and so this equation, vf prime, is going to become 2, but it's under the square root, so root 2 times the square root of 2gh, that quantity, over 3. That ends up being my initial velocity, so vf prime, my new final velocity, is just root 2 times vf, which is my original. The problem, though, does say that v is what we're defining as the original, so that means that my v prime would just be root 2 times v.